Right, we're going to look at infinite limits and limits at infinity. So an infinite limit, try and write a little statement here, is as x approaches c, the limit will approach either of the infinities, whether it's positive infinity or negative infinity. And what's happening there on the graph is a vertical asymptote. Right, so I can look at this picture of f of x here, and graphically, I can see that there is a vertical asymptote at 4. So when we talk about the limit as x approaches 4 from either direction, we can see what's happening. So here's 4, that vertical asymptote. From the left, the function is going to infinity. And then from the right, the function's going to negative infinity. Okay? If I look at g, we have a vertical asymptote at x equals 1. So this time from the left, it's going to negative infinity. And from the right, it's going to positive infinity. Okay? Erase my drawings here. So those are infinite limits. The sided limits are going off to the infinities. All right, but what about a limit at infinity? So this is as x is approaching the infinities. So as x approaches either of the infinities, the limit will approach a y value. We got to think horizontal asymptotes here. Or it'll be unbounded. So let's look at g. So the limit as x approaches negative infinity, the y values are going to negative infinity. And then as x is approaching positive infinity, the y's are also going to infinity. Okay, so we have a slant asymptote here. We don't have a horizontal one. But if we look at f, right, we do have a horizontal asymptote. So as x is going to negative infinity, we're approaching that line -2. And it's from both directions, actually, on this graph. Right, so we either will have the infinities as an answer, or we'll have a number. All right, so in pre-calculus, we could look at rational functions and we could analyze them, right? If we could factor the numerator and denominator, and we either had things cancel or things that didn't cancel, they meant different things. So if something canceled, we would say there was a hole in the graph. But if a factor didn't cancel, it's in that denominator. That was always a vertical asymptote. So if we aren't given a graph or a graphing utility to evaluate these limits, then we'd have to do it with some algebra. So this is the same function as above, I believe. So let's look at trying to factor it. So limit x approaches 4 from the left. Let's see, that numerator, I think I could take out a negative 2. Maybe it's not the same. I'll be left with x squared plus x minus 6. And then I can factor that further to being x plus 3, x minus 2. And then in the bottom, I could factor that to be x minus 4, x minus 2. So I could cancel out the factor of x minus 2. So there's a hole in the graph at 2. But I'm left with a factor of x minus 4 in the denominator. So there's a vertical asymptote at x equals 4. So when we talk about having to find that limit as it approaches from the left, we can substitute in a value. Like what if I want to substitute in something close? So how about, and we're from the left side, so how about 3.9? So if I substitute in 3.9, I would get, and I'm looking at just, because I know it's a vertical asymptote, I'm looking at, and my answer is going to be positive infinity or negative infinity. So I'm just looking at the sign. So 3.9 plus 3 is a positive number. And then 3.9 minus 4 is a negative number. Well, on top, we'll have a negative. On bottom, we have a negative. And so in the end, that's going to give us a positive number. So this limit is going to be going to positive infinity. Right? And then kind of the same idea from the right. So I'll write just the factored one we have. And let's plug in something like maybe 4.1. So I would have negative 2, and then 4.1 plus 3 is positive. 4.1 minus 4 is positive. So in the end, I have negative or positive, which in the end is negative. So that limit is approaching negative infinity. Okay. So let's see if we can do anything with these. Let's try and factor it. I don't think that numerator can factor. At the bottom, I can make that 2 times x minus 1. So that doesn't have us simplifying anything. So there's still a vertical asymptote of 1 because of that denominator there. So I'll start plugging in a number. So from 1 from the left, how about 0.9? So let's see, 0.9 squared is 0.81, and then 0.9 times negative 2 is 1.8, and then plus 5. All of that is going to be positive, and then 0.9 minus 1 is negative. So in the end, this is going to go to negative infinity. And then with the behavior of vertical asymptotes, if your factor, if the multiplicity is odd, then the function will approach the opposite infinity. So this is the same function, and I'm going to write this same function as part C. Vertical asymptote, multiplicity is odd, so function approaches opposite infinity. So because this left side was negative infinity, this side is going to be positive infinity. And you can verify that and plug in something like, I don't know, 1.1. So 1.1 squared is going to be, so I think it's going to be, well, obviously it's going to be positive, 2.2, and then minus 2.2 plus 5, so that's positive, right? And then the bottom, that's also positive. So positive infinity. Now, if the multiplicity was even, they'd be going the same direction. But okay, so here's a justification for asymptotes and holes. So if we have a case where we have substituted in a value, right, and we get a 0 in the denominator, so we have some number, and then a 0 in the denominator. That value, x equals c, is a vertical asymptote. But if it creates a 0 over 0, that would factor out, then x equals c is a whole, the x value of a whole. All right, so the limit definition of a vertical asymptote. So if the limit as x approaches c from the left of the function goes off to the infinities, or the limit as x approaches c from the right of the function goes off to either of the infinities, then x equals c is a vertical asymptote. Right? So let's find some. So with limits, we can do like a direct substitution in, right? But I don't really like doing that with the infinities. I like looking at, okay, I know when I'm going off to the infinities, I'm thinking horizontal asymptotes. So this function right here, if I were to multiply it all out, is going to give me some form of like an x to the 4th polynomial here. And I know based off of pre-calc knowledge, we are going to look based off the leading term. We're going to look something like this, where we're going off to the infinities in both directions. So as we're going to positive, x is going to positive infinity, the function is also going to positive infinity. Okay. I can do the same thing here as it's a polynomial. Based off that leading term, the function is going to look like this. Something like that, I should say. In behavior, I know we're going to infinity and negative infinity. And so as x approaches negative infinity, so is the y value. Right? Now the rational functions here, I can use the horizontal asymptote conditions, which I'll list down here below. But I can look at the leading terms, and then I compare the degrees. So the degree of the numerator is 2. The degree of the denominator is 2. So that means we have a horizontal asymptote at the ratio of the coefficients, which is 3 over 1, which is going to be 3. And so let's look here. I compare the leading terms again. So the numerator degree is 1. The denominator degree is 2. So we have a case where the denominator is greater. So that denominator is going to grow faster, which means we're going to go to 0. So the horizontal asymptote is y equals 0. So here's the different conditions, right? Either the numerator is going to be greater than the denominator degree, or it's going to be less, or it's going to be the same. So what we can do here is if the numerator is greater, like the degrees, right? It's greater than the denominator, we will have no horizontal asymptote. I'll put a star and say possible slant. If the numerator is less than the degree of the denominator, it's automatically y equals 0. But if the degrees are the same, the horizontal asymptote is the ratio of those leading coefficients. All right, so if we want the limit definition here, we could say if the limit as x approaches infinity for f of x is b, where b is some number, right? Or the limit as x approaches negative infinity for a function is b, then y equals b is a horizontal asymptote of the function. Right? So we have something called the intermediate value theorem. This is just a visual here. So if a function is continuous on a closed interval and the endpoints are not the same, then because it's continuous, the function is going to take on every single value in between the endpoints, right? That's all that is saying. And there's just a visual. All right. So let's look at some. So does the intermediate value theorem apply on these specific intervals of these piecewise functions? So is there a value x equals c on the interval -2 to 5 such that f of c is 1? So let's see. F of c is 1. Here's 1. And yeah, there is. But does the intermediate value theorem guarantee 1? It doesn't. Because the function is not continuous. From -2 to 5. Now, if we changed it and said from -2 to 1, we could say that because it is continuous on that interval. But the interval it's asking for, no. All right, is there a value from 1 to 6 where g of c is 3? And no, there is not. And we want, does the intermediate value theorem guarantee no, because while it's continuous here from 1 to 6, g of 3 doesn't occur within that interval at all. So that's not in the range of it. So no, IVT doesn't guarantee a value because g of c equaling 3 doesn't occur on this interval. All right, and that is all. So if you have any questions, let me know.